want to take a look at the effect of operating pressures on the performance of a vapor compression refrigeration system. So these systems operate between two pressures. The pressure down here in the evaporator, which is currently set at 1 bar, and the pressure up here in the condenser, which is currently set at 7 bar, and those are just the default conditions on the simulator here. So we're going to play with those numbers and see what effect it has on various things. So what we'll be interested in is the effect on the coefficient of performance over here, some of the state points, and particularly the refrigeration effect, which would be the heat added in the evaporator here. So I'm going to take a screenshot of just this little table so we can see what changes as we change those pressures. We'll just set that off to the side there. First of all, let's look at the temperature down here in the evaporator. So that's T4 and T1, and they should be the same because they're both in the liquid vapor region. So T1 is minus 26.4 and T4 is minus 26.4. So that's the coldest temperature in the cycle. Up here in the condenser, we see the temperature at 3 is 26.7 degrees, and the temperature at 2 is going to be a little bit higher, 35.8, because this is out in the superheated region. That's a little bit easier to see on the TS diagram because this axis is temperature. So the exit of the compressor here, which is the inlet of the condenser, is a little bit superheated, so a little bit higher. Anyway, that's the highest temperature in the cycle. So the lowest temperature in the cycle and the highest temperature in the cycle. And the reason I'm talking about temperatures here is because that's the main thing that the two operating pressures control. As we move those pressures up and down, it's going to change the temperatures in the evaporator and the condenser, and that'll determine the temperatures that our vapor compression system is working between. So let's make some changes here. First, we're going to increase the condenser pressure. So I'll take this condenser pressure and change it to 800 kPa, which is 8 bar. So that's gone up, and these values have changed, but of course hard to remember what they were, so we'll bring up our little screenshot over here so we can compare. And we take a look, and we see, first of all, the coefficient of performance has dropped from 3.6 down to 3.21. So that makes sense because this refrigeration system now needs to work harder because it's operating between a larger temperature difference, so it's going to have to work harder. There's going to be more work input. So if we look directly at the work input, the compressor work was 40.13, now it's 42.98. So the compressor is working harder, and our refrigeration effect has dropped from 144.57 down to 137.93. So the compressor has to work harder because it is moving this heat over a larger temperature difference. We'll also see that the temperature at the exit of the compressor, so T2 here, is now 40.6, and that's gone up quite a bit from 35.8. So we have a cycle that's now working harder over a larger temperature difference. So I'm going to hit reset so that we go back to our baseline conditions here, and now we're going to change the evaporator pressure. So instead of dropping the evaporator pressure, which will have a similar effect to increasing the condenser pressure because it will increase the spread between those two pressures, what I'm going to do is increase the evaporator pressure. So we'll go up to 200 kPa or 2 bar. So that's a fairly significant increase in the evaporator pressure. But you'll notice now the pressure difference is smaller, and so the temperature difference is also smaller. So we'll pull up our old baseline values here, and we see the coefficient of performance now has gone up. So it's almost 6, up from the original 3.6. So a much larger coefficient of performance because this vapor compression refrigeration system has less work to do to pump the heat from low temperature to high temperature. So our compressor work has gone down. It's only 25.8. Originally it was 40.13. The refrigeration effect has gone up, now 154, up from 144. The larger the spread between these two pressures, the harder this system has to work to move a unit of energy from low temperature to high temperature. So the coefficient of performance will go down as the spread between those two pressures increases.